All right, let's get right into it. We are looking at one of the absolute gems of the night sky, a gorgeous collection of stars called Messier 6, also known as the butterfly cluster. But it's more than just a pretty picture. This cluster holds a story, kind of a cold case file written in starlight. And today, we're going to be the detectives trying to crack it. So first, let's get our bearings. Our subject, the butterfly cluster, is about 400 parsecs away. That's roughly 1,300 light years from us here on Earth. Just to put that into perspective, the light we're seeing from it tonight actually started its journey back when the Roman Empire was in decline. And that incredible distance, well, that's our central challenge. So you gotta ask, right? How on earth can we learn anything detailed, like its age or what it's made of, from something so mind-bogglingly far away? How do astronomers actually read a story that's taken more than 1,000 years just to get to us? Well, it turns out they have a very specific set of detective tools. So here's our game plan for this investigation. First, we'll get to know our celestial subject, the cosmic butterfly. Then, we'll look at two of the key forensic tools in the kit, how we can tell time using starlight, and how to read its chemical fingerprint. After that, we'll apply these tools to our case study, M6, and see what clues pop out. And stick around for the end, because there's an unexpected plot twist. These peculiar stars that have left astronomers scratching their heads. Okay, first up, let's meet this cosmic butterfly. So what makes Messier 6 the perfect subject for our investigation? It's what's known as an open cluster. You can think of it like a stellar nursery. All the stars inside were born from the very same cloud of gas and dust at the exact same time. Now, for an astronomer, this is a dream come true. It means major variables like age and the starting chemical recipe are identical for every star. It's basically a controlled laboratory floating in space. So how do you even begin to investigate a lab that's 1,300 light years away? Well, you need your forensic tools. And our first one is a cosmic clock, and it's all about the color of starlight. We're looking at something called stellar color, or more specifically, UV color. Now, this isn't just about what you can see with your eyes. Astronomers measure a cluster's light in really specific bands, especially ultraviolet, or U, and blue, or B. And here's the genius part. The ratio between these two colors changes in a really predictable way as a cluster gets older. It literally acts like a cosmic clock. Younger clusters are bluer, and they get redder as they age. So how does this method actually work? Well, it's surprisingly straightforward. First, you measure the combined UV color of the entire cluster. Then, you turn to computer simulations that model exactly how a cluster's color should change over millions or even billions of years. And finally, you just find the point in the simulation where the model's color is a perfect match for what you observed. It's like cosmic forensics. And listen, this isn't just some neat trick. It's a fundamental part of modern astrophysics. Just as this research from Hancock and colleagues points out, this specific ultraviolet to blue color measurement is absolutely critical for figuring out how old these star-forming regions really are. It is one of the most powerful tools in the entire detective kit. But age is only one piece of the puzzle, right? Our second tool lets us figure out what these stars are actually made of. This technique is called abundance analysis, or spectroscopy. The idea is pretty simple, actually. You take the light from a star and you spread it out into a super detailed rainbow, which we call a spectrum. But here's the thing, it's not a perfect rainbow. It's got these little dark lines crossing it. And each chemical element, iron, calcium, you name it, absorbs light at its own very specific wavelengths. This leaves a unique pattern of dark lines that acts like a chemical fingerprint. Now, to get these fingerprints from M6, astronomers had to bring out the big guns. We're talking about the FLMS/Giraffe spectrograph, which is attached to the European Southern Observatory's very large telescope down in Chile. They had to painstakingly capture and then analyze the light from 44 different stars inside the cluster to build this incredibly detailed chemical profile of the whole group. So, we have our subject and we have our forensic tools. It's time to apply them to the case of Messier 6 and see what the evidence really tells us. First clue, the age. Using the cosmic clock, the team figured out that M6 is about 75 million years old. So in cosmic terms, it's basically a teenager. Second clue, the distance. The analysis confirmed the cluster's location at 400 parsecs away, making it a relatively close neighbor in our galaxy. And for the third big clue, we've got the chemical composition. This number here represents the cluster's metallicity, which astronomers write as Fe/H. It's basically a measure of how many heavy elements a star has compared to hydrogen. If the value were 0, its chemistry would be identical to our sun. This positive value, 0.07, tells us something really cool. M6 was born from a cloud of gas that was just a little bit more enriched with heavy elements than the one that formed our own solar system. But this is where the case takes a really fascinating turn. When the detectives looked closer, they found something weird. The cooler, more sun-like F-type stars, they were all pretty much chemically identical, which is exactly what you'd expect. They were the baseline. But the hotter, more massive A-type stars showed these wild variations in their chemical fingerprints. So even though they were all born from the exact same stuff, something was actively changing their surface chemistry. And that brings us to our conclusion, because just when you think you have all the answers, science uncovers an even deeper mystery. In this case, well, it's far from closed. See, the investigation of M6 didn't just confirm what we already knew, it actually uncovered a lineup of really unusual suspects. Several stars in the cluster were found to be chemically peculiar, which is a fancy way of saying their elemental makeup is so strange that it completely defies our standard models of how stars are supposed to work. I mean, check out this rogues gallery. You've got an M star, which has unusual amounts of metals, a Mercury-manganese star, which is exactly what it sounds like, and even one that is helium-weak and phosphorus-rich. Each one of these is its own little puzzle. Remember, they're all members of the same family, born from the same material, yet somehow they've evolved to become these complete chemical oddballs. And that leaves us with the final, tantalizing question of our whole investigation. It's often the things that don't fit the theory that lead to the biggest breakthroughs. So are these peculiar stars, these cosmic rebels in the butterfly cluster, showing us that there are hidden processes going on inside stars that are way more important than we ever realized? For now, the case remains open.